Students, this is Dr. Mocha, and today we're going to be solving paper 6, October-November 24, version 63. Now, a student investigates the cooling of water in different sized beakers. He uses apparatus shown in figure 1.1. Beaker A and beaker B have graduations as shown in figure 1.1. As you can see, in A it's 50, then 100, in B it's 100, 200, 300. So, record room temperature theta R shown on the thermometer. So as you can see, I have here 20 and 30 with 10 increments in between. So obviously it has stopped exactly at 2 increments after 20, that's 22. Describe one technique to use so that the temperature reading is as accurate as possible in the experiment. Well, the best thing always to measure or read any kind of reading is to always look at it at eye level, which is to view the temperature scale perpendicularly. Perpendicularly means you're at 90 degrees or at eye level. Can I just say at eye level? No, because this is paper 6. We're doing experiments, we're doing geometrical calculations as well. All right, part B, the student pours an estimated volume of 75 centimeter cube of hot water into beaker A. He uses the scale on the beaker as a guide. He puts the thermometer into the water in beaker A and records. In table 1.1, temperature theta at time t equals 0. He records in table 1.1 the temperature of the water in beaker A every 30 seconds. Okay. The student repeats the procedure for beaker B. His readings are shown in table 1.1, suggest one possible source of inaccuracy in the procedure, even if it's carried out carefully. Well, this one is, let's check. For instance, I can see that 73, 74, 75, okay. So 30, 60, 90, 120 at 75, they said they used a volume of 75 centimeter cube of hot water. So I can say that at 75 centimeter cube of hot water, it's difficult to estimate with large graduations on beakers. It's better to use smaller graduations on beakers to be more accurate. So I'm going to say that 75 centimeter cube is difficult to estimate due to large graduations on beakers. Okay. Next part, see, write a conclusion describing the effect of changing the size of the beaker on the rate of cooling of the hot water. Justify. Okay, so here we can see, of course, that when we change the size of the beaker, so we have beaker A and beaker B, and I just want to remind you that, here, let me go up. Beaker A was increments of 50, beaker B was increments of 100. As you can see, the reading in beaker A is much more accurate than in beaker B, which has the increments or the temperature changes a bit more. So what we're going to say is that beaker A had increments of 50, while B had increments of 100. Hence, here I'm going to write my reason, but I have to take some data from the table to as proof to my answer. So at 0 seconds, A was 82.5 and B was 80. All the way at 180 seconds, beaker A went down to 73, but beaker B went to 63.5. This is due to the large surface area, okay? So the temperature change in beaker B was larger, going from 80 degrees Celsius to 63.5 degrees Celsius in 180 seconds, while of course you should not go beyond the lines assigned to you, but because my handwriting is large and I'm writing on a screen, that's why it's gone a little bit further, while beaker A went from 82.5 degrees Celsius to 73.0 degrees Celsius, showing greater cooling rate in beaker B. A bit of chemistry here, right? All right. Question D. Students in other schools do the same experiment using identical apparatus. Say one variable that they need to control in order to obtain readings as close as possible to the readings in table 1.1. So, for example, it has a 1 mark and I need one variable. So I'm just going to write that I need to, of course, keep what in control. They said that I've used 75 centimeter cube of water, so I have to keep that the same. So I'm going to write that I need to use the same volume of water. Okay, you can use other answers as well, like the initial temperature that you're going to start with, the temperature of the surrounding. Okay. Part E, calculate the average cooling rate X for beaker B. Use the readings for beaker B in table 1.1 and the equation X equal to theta 0 minus theta 180 over T, where T is 180 seconds, theta 0 and theta 180 are temperatures of water at T equals 0 and T equal 180. Include the unit for the cooling rate. Okay, so for this part, we're going to work with beaker B. So we need to go up and find at T0 and at T180 for beaker B, what was the temperature? 80, 63.5. So X equals 80 minus 63.5 over 180. Okay, let me do it on my calculator. So 80 minus 63.5 divided by 180. The answer I got was 0.0917, three significant figures. Another student thinks that, yeah. And of course, I forgot to put the unit. So degrees Celsius per second. Because here they put for me, this is degrees Celsius for the temperature and second for the time. So degrees Celsius per second. Another student thinks that more thermal energy is lost from the surface of the water in beaker B than from the sides of beaker B. Suggest an additional experiment that she can do with beaker B to test her idea. Well, this is very easy. I can just put a lid on. So add a lid on top. Or if someone wants to test the sides, they can add some insulation on the sides. Okay, next, suggest how the cooling rate of the water in beaker B in this additional experiment compares with the value of X in E if her idea is correct. Well, definitely the cooling rate, he said the value of X in E, okay, will be less than X because we just insulated it, right? Or we covered it. All right? Okay. Basically, that's all for this question. I'll see you in the next question. Have a good day.